So why does water move in porous media, for example, or soils? And we, of course, have our wonderful equation that the flow of water is equal to the negative of the conductivity times the area times the gradient and potential. And this is what we call Darcy's law. Okay, so we've seen this equation before. Now, what I want to focus on today is the total potential. Okay, that is the gradient in that quantity is what gives rise to movement. So we know that if we had an aquifer, and let's say that it had a slope to it, so this is our water level, then this point would be at the water table, and this point is at the water table. They both have a pressure of the water is equal to 0 at both that point and that point. But we also know that the water would flow in this direction, from higher potential to lower potential. So immediately what we see is we have two things going on. We have elevation, and we have pressure. Okay. And the total potential, which we use the symbol capital H for, is equal simply to the sum of the elevation plus the pressure. And we're measuring this pressure in units of head of water. So what does head mean? Head is the amount of water, the height of a column of water that would be supported by that much pressure. Okay? So if we wrote it in terms of pressure, pressure equals the density of the liquid times the acceleration of gravity times the height of that column of water. So when we're converting between a true pressure measured in newtons per square meter, that's going to be related to the height of water we see times the density of water and the acceleration of gravity. So we use head because it's very convenient in units, because then we are measuring elevation in the same units as we're measuring pressure. And then the sum of those two is the total potential. Now, what about this z a little bit? We have to define where z equals 0. So what we can do is we can assign an elevation, any elevation we like actually, that we can call the datum. And that is defined by z equals 0. Okay, that's the datum. Then all elevations will be measured relative to that datum. Okay? And the point is that water moves not due to the absolute value of the potential, but rather the local changes. And so as long as we well represent the changes in elevation, we're in fine shape. So that's how we can define the datum to be any place we like, so long as we're consistent. So then when we look at this total potential, let's take a quick look at what would happen in a glass of water. So here's our water, here's our water table. And let's just put the z equals 0 here, and that'll be our datum, okay? And what we can say is that at the top of the water, by definition, it's not holding up any water, so the pressure head here is equal to 0. So what we have here is a h equals 0 here and a z equals 0 there. This system, the water's not moving, it's what's called hydrostatic. And I really want you to keep focus on this word static. That means it's not moving, it's still. So we'll talk about steady state later, which is a little different when things are moving at the same rate in time. Here we're only talking about things that are actually static. So when things are hydrostatic, that means there's no movement, that means there's no flow, that means the total potential has no gradient, and therefore the total potential is equal to the same value everywhere. Aha! So H, capital H, is equal to a constant in this whole cup of water. And here we can identify that if our cup of water has a height L, then that H is equal to L. And how do I know that? Because I can go here where pressure is 0 and H and Z is equal to L, and I get H equals L. Okay? So I go to where I know the pressure and I know the elevation, and that's my total potential. And now, as it turns out, that total potential is known throughout this problem. What's going on is that the pressure in our vessel increases with depth, whereas the depth itself, Z of course, is decreasing. But the sum of the two, H equals little h plus Z, is a constant. So as we go down in our vessel, the head increases. But as we go down in the vessel, our elevation decreases. And they cancel each other out to provide a constant total potential. So when we're talking about the movement of liquids, we're always thinking in terms of the total potential and how that total potential is distributed. If I put a hole in the vessel right here, oops, I drop the pressure here, and now I get flow towards that lower total potential. So keep in mind, total potential, it's just elevation plus pressure head.